Let's see.
Hi, Sky. I can hear you.
You
Can
can
you
hear
hear
me?
me okay?
Yeah, I can hear you. Wait, keep talking real quick.
Sure. Let's keep talking. We're going to bring me on. We're going to talk about some amazing astrophysics stuff because I know that your viewers have a ton of questions for us.
Oh, yeah. No, I'm sure. They've been waiting for this moment because they've been asking a bunch of questions, which are very good questions, but I have to keep telling them I don't know.
Yeah, that's how it is, and good for you for saying that. Some of the most powerful words in the English language are "I don't know" when you can admit what it is you do and don't know.
Yeah, I don't know a lot about any of the quantum stuff. Not to your level for sure. But we were just watching our past interviews where you've been on here, and everybody was like, "This guy's amazing." So I gave them a head start. And guys, you can check out who he is. All of his information's in the guest command. He has written books, and he's an astrophysicist. Really great with that theoretical stuff. Cosmology is a big thing too. So why don't we start with your name? It all starts with a bang, or it starts with a bang. Let's be correct here.
Yeah, back in this is ancient history now. Back in 2007, I was going to start a blog. I had gotten my PhD in physics the year before. I was working as a research astronomer at the University of Arizona, and I had, for me, what was a tremendous crisis. Like, here I was working on the thing that I had worked towards, that I had dreamed about working on, and I had my choice of a few different positions on where to go, and I chose the University of Arizona because it had the professor I wanted to work with and an overall very strong program where there were three people that I was very excited to collaborate with. And in the time that I accepted the position in, I think, April or May was officially, and when I arrived in July or August, two of the professors had left, and the one that I was nominally working for as my principal investigator, as my lead professor, told me that he was going to be taking over as the PI for this other mission, and he didn't really have time to work with me. So I was kind of going to be on my own. And so that's what I was doing, is I was having a crisis saying, this is what I want to do, and here I am doing it, and it's not what I wanted to be doing. So what do I do? Well, what else was I interested in? One of the big things is I realized I know this story now. I have all of this knowledge about cosmology, astrophysics, the universe, how it all comes together, how it came to be. And this is a story people should know. This
Mm-hmm.
is a story that if you ask a random curious person of any age on the street, they'll wish that they knew the answers to this. They'll wish they knew the story behind this. But they've always gotten, or when they've inquired about it, they felt that it was inaccessible to them, that it was intractable, that they themselves would have to go through what I did, which is, 4 years of undergraduate and then years of graduate school to get their PhD and then further years of research to become adept at it.
Mm-hmm.
That's not true. You don't need that. So my goal was to tell the story of what we know and how we know it about the universe to as wide an audience as possible, to do it in layperson's terms, but not with a layperson's understanding of it. Let's give people the full knowledge that we have. Let's walk everyone right up to the edge of what we know and what we don't know, and bring everyone on board, because this story is not only for everyone. The story of how the universe came to be, how it operates and got to be the way it is today, and where it's headed in the future, this is a story that's common to everyone. This is a story, a cosmic story that every single one of us shares. So, Starts with a Bang for me was the right title to say, you know what? Let's put this information out there about where we can say our observable universe began, how everything came from it, and when we have to even talk about where that bang might have come from.
Let's start there because no one's saying anything just yet because I think they're still coming in right now. But let's start there. So let's talk about, because a lot of people know, okay, so there was a big bang. And a lot of people don't subscribe to the idea, but a lot of people do. So what maybe came before? What are some of the wonky ideas, or I mean, not wonky in that. I mean, again, something coming from nothing.
Well, let's before we get into something coming from nothing, let me set up why you would even think the Big Bang was reasonable. When you sit here from our perspective on Earth in the Milky Way galaxy, if you wanted to understand the universe, one of the big things would be to look out at objects beyond Earth, beyond the sun, and beyond our own galaxy. And when we look at that, what we find is we've got ourselves, Andromeda, the Triangulum galaxy, and maybe 60 other small galaxies all bound together in our local group. The majority of these galaxies are falling towards us. We think that's because of gravitational attraction, that over lots of time, these galaxies have come, fallen towards us. Gravity's pulled them together. Fine, that makes sense. When we run our simulations, we find that we've got billions and billions of years to go, but after they go by, we will in fact all merge together into a giant, enormous elliptical galaxy, which we've already named, by the way. We call it Milkdromeda. I don't know why we get top billing. We're only the second biggest. So then you look out at all the other galaxies. You look out at the more distant galaxies, and some of them are isolated. We call those field galaxies. Some of those, like us, are bound together into these groups of galaxies, and some of them are bound together into these enormous clusters of galaxies, where instead of 2 or 3 Milky Way sized galaxies like we have, they have like thousands of them.
Mhm.
So some of these clusters are really enormous. The Virgo cluster is the closest. The Coma cluster, which is also pretty close, is even bigger. And some of these have like maybe as many as 10,000 Milky Way sized galaxies. They're really huge. The thing is, from where we are, when we look out at all the other galaxies and groups of galaxies and clusters of galaxies in the universe, we find two things. One, they're all moving away from us. And two, the farther away they are, the faster they appear to be moving away from us.
And why
So
is that
why would this
happening?
be?
Yeah, why?
Why would this be? Well, in general relativity, right, there are a few things you can do to solve Einstein's equations, that you can come up with solutions under certain conditions to Einstein's equations. One of those says, let's imagine that you just have a universe and it's full of stuff, matter, radiation, whatever you want. Universe is relatively uniformly full of stuff. What do you do about that? The answer is, well, if you try and solve it, this was done by Alexander Friedman, a Soviet scientist in 1922.
Hmm.
Alexander Friedman was the first one to solve these equations. And what he showed was that if you solve it like this, then your universe cannot be static. It must be expanding or contracting. And if it expands, right, if we're over here and we have space a certain distance away, if the space between these galaxies is expanding, where gravitation, like it has in our local group, has overcome the expansion of the universe, if you look between these bound structures, the universe should still be expanding. So all of the light coming from this, as the universe expands, as space stretches, the light should stretch, and that should make it look like it's moving away from us. The farther away you look, the more the universe has expanded. So then, Hubble came along. He observed all of this for all of these galaxies. He plotted out Hubble's law, which showed that the farther away a galaxy is, the faster it appears to be receding from us. All of this fits in with the concept of the expanding universe. So fine, the universe is expanding, which means as time goes on, it gets bigger and bigger, and things get farther and farther apart.
So someone
So you
actually,
said
well,
you
someone,
said where'd the Big Bang come
right,
from?
right. So I mean, is it have a single point? Someone actually asked that in chat, 'cause now questions are coming in left and right. So someone actually said, does it come from a single place or right here? So Jack said, so where would the center of everything be? From what point is it that everything is moving away from?
Well, I don't know that that's really a fair question. Imagine the way I like to picture the expanding universe is, imagine that they've got like the largest oven you can imagine in space, in zero gravity. You've just got this huge oven. preheated to 350 degrees, and you have this enormous ball of dough,
Hmm.
also in space with the yeast and the sugar and everything you need in it. And also, we put raisins all throughout the dough. Then you put the dough in the oven and you let the dough bake. Well, it's going to expand in all directions. Now, for a ball of dough, you can say that's where the center of the ball is. But what if all you were on one of the raisins and you couldn't see the dough? You could just see the other raisins, and not all of the other raisins, only the raisins within a certain distance of you. If that were you, you would conclude that your raisin, was the center of everything because it was the center of everything you could see. But without being able to see the full ball of dough or all the raisins everywhere, you wouldn't know. From where we stand, we say we have every right to claim ourselves as the center of the universe, but so would anyone else looking everywhere. So, what we think is that there is no center of the universe. We say that all locations have equal claim to being the center. But realistically, if we extrapolate back to the Big Bang, and maybe I should get there next, um, the more accurate thing to say is that the Big Bang didn't happen at one location. It happened everywhere in space at once. It happened at a single time, but not at a single place.
Love it. That's awesome. Everybody's saying already. His explanation is good. He's amazing. But scientifically, is there an actual center though? Even though we'll never know. No. So it's based on what he's saying. It's your frame of reference. So, right? I mean, we're gonna think that everything is moving away from us. That we're kind of the center, even now, right?
It's
Or
really hard because if we could go to a distant galaxy, not like a nearby galaxy, but one like many
billions.
millions of light years away, maybe even billions of light years away, we could observe what does the universe look like from there. And if they saw something that is large scale similar to what we saw, then we would say no, there is no actual center. Every place has equal claim and no claim to being the center. So without being able to observe from another location, we can't really answer that question. We can tell you what our theories predict, and they predict no center, but there could be something more complex that would be revealed with observations that we just can't make right now. But I want to make sure everyone understands that the idea of the Big Bang is today we observe the universe is expanding and cooling, which means if we look backwards in time instead of forwards in time, then the universe should have been smaller.
Mm-hmm.
And also because the energy inherent to light is defined by the light's wavelengths, when your space is smaller, the wavelength of light was smaller, which
Mm-hmm.
means your light was more energetic, and therefore your universe was hotter. So you go back in time to when the universe was smaller and hotter and denser, and smaller and hotter and denser. And eventually, you would get photons whose wavelength was so short that it would knock electrons off of neutral atoms. You would not be able to have neutral atoms in the universe. Everything would be this ionized plasma. And guess what? We see the leftover glow from that time, from 13 and some odd billion years ago, when you cooled that you could form neutral atoms for the first time. We actually see the radiation that was released from that point. That's what the cosmic microwave background is.
Hmm.
You can go back even farther to say, okay, what about it must have been hot enough that you could have no atomic nuclei, where you would blast apart anything that tried to have bound protons and neutrons? Well, we get that too, because that means the universe cooled to a point where all of a sudden, for the first time, nuclear fusion could occur in the hot early universe without things being blasted apart. Guess what? We've discovered pristine gas that had never formed stars from left over from the Big Bang. The first gas of this was discovered in 2011, and it was found to match exactly with the predictions of the Big Bang. 75% hydrogen, 25% helium, about 0.0000001% lithium, and nothing heavier than that. That's what we predict you form in the early universe. That's it. So you might say, okay, well, now I want to know, because I'm clever, I know these extrapolations work. I want to go all the way back to a
Right.
singularity, to where all the matter and energy in the universe was compressed into a single point. And that's what I want to call the Big Bang, and that's the very beginning of the universe. And fair enough, if you want to extrapolate that way, we did. When we first conceived of the Big Bang, when Lemaitre did it in 27, when George Gamow did it in the 40s, when subsequent people like Alpha and Hermann worked on it in the 40s and 50s, this is what they thought of. This is the hot early state they thought of. They thought of a singularity. Lemaitre called it the primeval atom. George Gamow talked about it as like this place of infinite heat and density, and other people have talked about it as a singularity. The thing is, we know that there wasn't an arbitrarily hot, dense state.
Hmm.
And we know this by looking at the imperfections in the cosmic microwave background itself. If we had reached that hot, dense state, we would see certain types of fluctuations, of temperature fluctuations, and we would see certain magnitudes of temperature fluctuations, and we don't see them. What we see is about 30,000 times smaller than you would expect if you had a singularity.
Wow.
Therefore, we think the Big Bang can't extrapolate all the way back to a singularity. Something else had to happen at some early stage, at some hot, dense stage to set that up that has nothing to do with a singularity. That's the theory of cosmic inflation. Cosmic inflation, by the way, has been around for almost 40 years. We have 6 tests that we figured out how to perform on them, and 4 of them have actually validated cosmic inflation. The other 2 were not sensitive enough to measure yet, but we're still working on it. This is something that almost nobody knows. Why doesn't anybody know this? Probably because nobody like me has been there to tell them to translate from theoretical physics into plain English. But
Right.
you're in luck because I'm writing a book on this, and it is going to be 10 chapters long, and I'm in the middle of chapter 8 on the first draft. So with any luck, you'll all be able to read a book titled something like Before the Big Bang next year.
Nice. That's awesome. And so wait here. There's some questions relating to that. So someone said, uh, that's awesome. I didn't know you were working on a new book. That's great. And we'll have to add that in the command once it's out. Someone said, "Isn't it so? So what happened before? Like, where was all this coming from? Can we truly confirm the Big Bang happened and that something really actually did come from nothing?" So now we're going back
Okay,
even further than the cosmic microwave background radiation, and you know.
okay. Well, let's talk a little bit about cosmic inflation then, because
Okay,
this is
I'm all about it. Let's do
a
it.
lot of people, they've heard someone like Lawrence Krauss say the universe came from nothing.
Mm-hmm.
And that's fine, but I want to be a little more precise than that. When some people think of nothing, they think about it the way a physicist does. A physicist will say, when I say nothing, I mean physical nothingness.
Right.
Take space and take all the matter out of it, take all the radiation out of it, take all the energy out of it, take everything that would curve space very far away. So all you have is blank, empty space with nothing in it. But you still have space, you still have time, and you still have the laws of physics. That's what we mean by physical nothingness. That is very different than what some people mean when they say nothing, where they say, I want you to take away space. I want you to take away time. I want you to take away the laws of physics. Those all sound like something to me, and I want absolutely nothing. Well, you can imagine that, but that no longer makes any physical sense. We can't make predictions about that. We can only do physics with the laws of physics that we have. anything else is just going to be idle, philosophical, untestable, speculation, which you're fine to do. You can ask questions like, what was the universe like without space and without time? And you can try and ask those questions, but that doesn't make physical sense, right? How can you talk about what's happening outside of space? Space is all there is.
Right.
How can you talk about something that happened before there was time? The word before doesn't make any sense without the concept of time.
Time. Right.
So when we talk about nothing, we're saying, let's assume that we still have space and time, and they have to obey some laws in order for us to be able to make predictions. Well, one of the weird things that we know exists today is, some of you may have heard of this term, we call it 0 point energy. Or maybe when we talk about the universe itself, we call it vacuum energy. We talk about the energy inherent to empty space itself. Some of you might think, oh, that's got to be zero, right? You take everything away, and the lowest possible energy you can have in your system is a zero energy system. Sure sounds reasonable, doesn't it?
Hmm.
Except that isn't how everything works. There are a lot of physical systems where the ground state energy, or the 0 point energy, the lowest energy state something can reach, is not zero. It's some finite positive value. We have this, by the way, in our universe today. Those of you who've heard about dark energy is a certain non-zero amount of energy inherent to the fabric of space itself. It's causing the universe's expansion rate to accelerate, which means if you look at a distant galaxy, you would expect, right, in the Big Bang, right, the universe is expanding, it has all this matter in it. You would expect one of three things to happen. Either gravitation wins, right? Gravitation, right? The universe starts expanding and things are getting farther apart, but everything gravitates. Eventually, the expansion will reach a maximum size, turn around, recollapse, big crunch. One possibility.
Hmm.
Or you can imagine on the other end of the spectrum, same deal, starts off, lots of expansion, lots of gravity, but gravity doesn't quite have enough to win, the expansion wins. So things slow down, slow down, slow down, but they keep expanding away forever. That's the big freeze. Or you can imagine you live right on that nice knife edge. You can imagine, right, like your Goldilocks, right?
Hmm.
The porridge isn't too hot, the porridge isn't too cold, the porridge is just right. You can imagine that the expansion happens and gravitation works to balance it. And so you get an asymptote. The universe's expansion rate asymptotes to zero, and things get farther and farther apart, but they never fully recollapse, or they never speed away forever and ever. What you'll be is you'll be right on that edge. We call that a critical universe.
Ooh.
Then you have what we observe. What did we observe? It's a fourth option. The universe looked like it was doing this critical thing, and then all of a sudden, about 6 billion years ago, the universe's expansion rate started speeding up, which means a distant galaxy that was getting farther away, but it was slowing down, slowing down, slowing down, slowing down. Now it starts speeding up, speeding up, speeding up, speeding up away from us.
I'm showing them the rubber band of the expansion.
Very nice.
I'm such a nerd. So now you've got this expansion that's speeding up. So, and you've defined kind of that nothing actually is something. So what
So
do you
now
do with
let's apply
this?
this to
Yeah.
the earliest stages of the universe. Before the Big Bang, imagine, instead of having your universe filled with matter and radiation like it is today, instead of being filled with stars and galaxies or protons and electrons and dark matter, imagine instead of that, you have this energy inherent to space itself, but not the tiny value of dark energy we have today, but an enormous amount of energy inherent to space. That will cause your universe to expand exponentially. It means that every about 10 to the minus 35 seconds, based on the values we think inflation had, your universe's scale, the distance scale, will double in size. So after 10 to the minus 35 seconds, your universe is twice as big as it was before. And then after 2 times 10 to the minus 35 seconds. It's 4 times as big as it was initially. And then after 3 times 10 to the minus 35 seconds, it's 8 times as big as it was initially, which means if you wait 10 to the minus 34 seconds, your universe is over 1,000 times as big as it was initially. If you wait 10 to the minus 33 seconds, your universe will be like 2 to the 100 times, or about 10 to the 30 times as big as it was initially. If you wait 10 to the minus 32 seconds, your universe, that's enough time to take something that was the Planck length, the smallest possible physical length that makes sense. It would be much larger than even the observable universe today is.
Hmm.
So inflation will take any universe you had, as long as it starts inflating, and it will fill it with energy inherent to space. It will take any particles that pre-existed and drive them all apart, and it will stretch your universe flat and give you the same temperature or energy density everywhere. Then later, at some point, inflation ends where we are, and all of that energy inherent to space gets converted
Hmm.
into matter and energy particles. And that is how we think inflation came to an end and started the hot Big Bang, not at a singularity, but from a hot, dense, but not arbitrarily hot or arbitrarily dense state. There's a limit, and we can measure that limit by looking at the fluctuations left over in the glow from the Big Bang.
So, T-Flex had a good question. So, is the actual expansion, as demonstrating with my rubber band, is it of space-time, of matter, or both? Like, what is expanding in space?
Well, so you brought up a really good point here. What is expanding is this fabric of space itself, which means if you take where you are as an imaginary point and you take where anything else is, including nothing, that's also an imaginary point. We're talking about how the distances between these 2 points evolve. And that's how we measure the expansion of the universe. In our universe today, we actually have to look at objects. We have to look at, okay, here we are, there's a galaxy, this is what's expanding. So you measure the distance from us to this other galaxy, and that's the thing that's expanding. In the early universe, we don't have that. All we have is the remnants of inflation. All we can see of the Big Bang is the aftermath of a bang. We don't see the bang itself.
How
So
close? How
this is
close
what
do
we
we
have to do,
get?
is we have to play detective with the clues we have left today.
And how close do we get to, that point that it actually happened? How far can we see back? I'm sure you probably know this number off the top of your head.
Yeah, so by looking at the light left over from the Big Bang, we're seeing the universe as it was 380,000 years after the Big Bang. By looking at the leftover heavy elements, the light elements, those were all formed within about 3 or 4 minutes after the Big Bang. But if we could look all the way back to find the gravitational waves, right? I told you there were 6 predictions of inflation. We found 4 of them. There are 2 left. One of them is, how curved is the universe? What's the spatial curvature of the universe? We expect that, yeah, inflation will stretch it flat, but there will also be fluctuations away from perfect flatness that show up somewhere between 1 and 100 parts per million.
Hmm.
We've gotten down to about 1 part per probably 500 or so, but we need to get down to about 1 part in 10,000, 100,000, a million to be able to measure it. The other thing we could measure, though, is gravitational waves that were produced during inflation. There are experiments searching for that right now. And if we find that, that would take us back to the last moments of inflation rather than the first moments of the Big Bang. So that would be the ultimate thing we could observe that would give us a clue about inflation. Right now, We haven't seen that yet. We haven't gotten a confirmed positive signal from that. Some of you might remember the Bicep 2 fiasco from a few years ago, where they claimed to detect gravitational waves from the earliest stages of the universe, but it turned out that they had done something faulty and that they hadn't detected that at all. So that's that's something we're still looking for today. They're on to Bicep 3, and there are many other experiments looking for similar observables right now.
And there's actually two good questions here. So the people are asking really, because I told them like I can't answer these. So they're a lot of Skynets just like I just want to get these out because we have you. Um, Someone said, "Do you think the 0 point energy is being stretched thinner as space expands?"
This is something we can measure. No, I don't. So we think that there was a huge decrease at the end of inflation, right? 0 point energy was way up here and then plummeted, boom, down to its present tiny value because all of that giant energy drop is where the matter and energy in our universe came from. All of that got converted into particles, antiparticles, and radiation. And that's how the hot Big Bang came to be. But there is this tiny amount of energy left inherent to space itself. One of the things I used to research was if whether dark energy, right, this energy inherent to space, whether it's truly a constant or whether it might increase or decrease.
Yeah, be dynamic.
um, we give it what we call an equation of state, right? Matt, we in physics we say like, okay, there are these different parts of the equation and they're related in such and such ways. Um, to simplify it, there's a parameter, we call it W. W is something that contributes to the expanding universe, and the value of W tells you how. For matter, W is 0. For radiation, W is plus a third. And for energy inherent to space itself that doesn't change over time, W should be exactly -1. So when I started doing my research after I got my PhD, so I'd done some research before. After I got my PhD, we knew that W was -1 plus or minus about zero point 0.3. That was a big deal because these different values of W normally go in increments of 1/3. Matter is 0, radiation is plus a third. If we had cosmic strings in the universe, that would be minus a third. If we had domain walls in the universe, that would be -2/3. And a cosmological constant or vacuum energy would be -1. We've now constrained W to be -1 plus or minus zero point 0.08.
Mm-hmm.
The W first satellite, which is slated to launch in 2024 and is going to be NASA's next astrophysics flagship mission after the James Webb Space Telescope, is optimized to measure, among other things, the value of W. And we're expecting to see that it's -1 plus or minus just 1 or 2%. But if W changes, if either it changes over time or it's different from -1, then it could still increase or decrease. But what we observe is consistent with it remaining exactly the same, with no evidence that it tilts or changes over time.
Yeah, someone asked a question. Could dark matter be the intersection, sorry, the chat just moved, of gravitational fields as it appears mass without mass?
So this is a different thing. This is not
I
dark
know
energy.
this is
This
not.
is
Yeah,
dark
this is
matter.
dark matter. You want to distinguish the real quickly between because I there's so many good questions and so um can you maybe distinguish between dark energy, dark matter?
Right. So dark energy, when we talk about this, dark energy is a form of energy that's responsible for the expansion of the universe speeding up. Like I told you, different galaxies, as they're farther away, they appear to expand from us faster and faster. They appear to recede faster and faster. Dark energy is the explanation for that. Dark energy doesn't clump, it doesn't cluster, it just appears to be energy inherent to space itself. And only in the places where you have enough mass that, if you dropped a little particle down, it would fall into your mass rather than getting caught up in the expansion of the universe. Only in these places, like our local group, can we neglect dark energy. Any place else between the galaxies, between the groups, between the clusters, dark energy might be the only effect that matters. Dark matter, however, does clump.
Mm-hmm.
Dark matter we find in clumps and clusters and filaments. Anywhere we find normal matter, and some places that we don't. So dark matter starts off permeating the universe relatively evenly, just like normal matter does. But wherever you have these tiny imperfections, an overdense region is going to attract more normal matter and dark matter. An underdense region is going to give up its normal matter and its dark matter. And then we'll see the dark matter today should be clumped together. The difference between dark matter and normal matter is that dark matter is dark because it doesn't interact with light or normal matter. So the only way it interacts is gravitationally. If the only way we interacted was gravitationally, we wouldn't have become a spiral galaxy, because when matter collapses, it splats together, right? Matter and matter, we don't just pass right through, we interact.
Mm-hmm.
That's the electromagnetic force driving that. Dark matter doesn't interact electromagnetically. We also don't think it interacts via the nuclear force,
Hmm.
so only gravitationally. So while we have our spiral galaxy in like a disk shape, we expect there to be a much larger, more diffuse halo of dark matter surrounding not just us, but every galaxy. We see the effects of gravity, particularly on large scales, that are consistent with dark matter existing. And this shows up in simulations of structure formation, observations of gravitational lensing, collisions of galaxies and galaxy clusters. So we have a whole suite of evidence that all points to dark matter's existence, but we haven't been able to directly detect it or find which particles, if there are particles, that are responsible for it. But dark matter does clump, and it is distinct from dark energy. And I just wanted to make that distinction for every one of you.
Yeah. And let's see. So now this is going to a whole different part of this too, but it does have to do with the Big Bang. So we're kind of going all over the place, but you can handle that. Does the Big Bang birth a multiverse scenario, or would each universe have their own version of the Big Bang?
Okay, so I'm going to give you my version of it, which is extremely conservative, and then we can talk about what other people who are more willing to speculate wildly will say about that. So imagine this inflating universe. I told you it takes less than 10 to the minus 32 seconds to go from the tiniest quantum distance scale to something bigger than our observable universe today. Well, inflation, because we live in a quantum universe, has to be a quantum field. So think about this as we've got a very flat hill top, and at some point it'll curve down and roll into the valley. As long as you're up on this hilltop, your universe is inflating. So if you stuck a ball on top of this hilltop and you let it do its thing, it would stay, and maybe it would start rolling very slowly. So you're inflating, you're inflating, you're inflating, and then you roll down the hill and boom, inflation comes to an end, you get the hot Big Bang. Does inflation end everywhere at the same time? The answer can't be yes. And the reason it can't be yes is because I just told you inflation has to be a quantum field. One of the things quantum fields do is they spread out over time. You know about quantum indeterminism, where if you take a particle and you put a particle down and you leave it down there for a certain amount of time, what happens? That particle is going to what? it's not going to be in the same spot,
Mm-mm.
right? You have the Heisenberg uncertainty
Right.
principle. Depending on how you measure it, when you measure it, it might be here, but it might be here or here or here. There's a probability distribution, and that probability distribution spreads out more and more over time. So now you say, okay, here we are on top of the hill, and this inflationary field is spreading out. In some places, you'll go farther up the hill. In some places, you'll be at the same spot where you were on the hill. And in other places, you'll be closer to the edge of the hill where you
Mm-hmm.
roll into the valley. In our part of the universe, we know inflation made it to the edge of the valley and rolled down, but
Right.
there ought to be plenty of other regions where inflation went further up the hill and the universe kept inflating. All scenarios, all viable scenarios of inflation that give us a hot Big Bang also give us, when you apply quantum physics, they give us this scenario that we call eternal inflation, which is to say, wherever inflation comes to an end, there's another region where it not only doesn't come to an end, but it continues inflating, which means now I have all these new regions that are inflating. A bunch of them come to an end, but as long as there are still more regions where inflation continues, we still inflate more and more. So the necessity is there have to be regions like ours where we've had a big bang and everything got converted into matter and energy, but there are also surrounding that regions where inflation is still going on. And yes, in some of those regions, inflation will come to an end. But between the regions where inflation comes to an end, you have more inflating space, pushing them exponentially apart. So when you run the math, you find out, you know what, these different bubbles that form, if you think about where the Big Bang occurs as a bubble,
Mm-hmm.
they won't ever collide because the inflating space between them expands faster than any post Big Bang universe can. That's the most conservative idea of a multiverse. And to me, it's an unavoidable consequence of two ingredients. One is cosmic inflation, which was theorized in the early 80s and which we've had plenty of observational evidence for since the 90s. And the second ingredient is quantum physics. If we live in a quantum universe and we have cosmic inflation, then yes, we live in a multiverse where many different regions of space have had their own Big Bang and we're in one of them. So other people say, well, now it's speculation time.
Mm-hmm.
I'm going to speculate a few things. One of the things I'm going to speculate is that these different universes, these different Big Bangs that take place in the multiverse, they have different laws of physics. I don't know why you would say that. It's possible. There's no evidence. We think that the laws of physics are determined at some super high energy, which we know we don't reach during or at the end of inflation because we've got that observational limit on the maximum temperature of the universe. Some people appeal to string theory arguments. I don't know why you would. It's not like string theory occurs at the low energy, is relevant at the low energies that the universe gets up to in the hot Big Bang. But that's something some people say. Some people say, what if we have different laws of physics in different regions of the multiverse? I say, well, then we do. But I don't have any reason to believe that that would be the case. Other people say, hey, you know what? If these different regions of the multiverse all come to an end and you get these big bangs in all these different places and the universe is expanding exponentially, so you get this exponentially larger and larger and larger number of possible universes over time, maybe you'll get a universe that's unfolded exactly like ours had, where you and I are having this conversation 13.8 billion years after a Big Bang over there on the planet Earth with the same exact properties as we do now, except in the other universe, I had to pick my nose really bad and I gave myself a nosebleed, and every one of your followers just watched me bleed to death out of my nose on the internet. Um, you never know. It's possible. But in order for that to be the case, in order for those infinite parallel universes to happen and be real, it's not enough to say, oh, you have inflation in quantum physics and you get enough multiverses to do this. It won't happen because the number of possible combinations of quantum interactions that happen in a universe increases faster than even the exponential growth rate of inflation. So, in order for that to be true, in order for that parallel universe hypothesis to be true, you would need for the universe to be infinite. Either it needed to be born infinite, which it could have been, but we don't know,
Mm-hmm.
or you needed inflation to be going on for an infinite amount of time. We know that it will go on arbitrarily far into the future, but that's not the same as saying it has gone on for an infinitely far amount of time in the past.
Right.
So that's the way some other people talk about the multiverse. And well, maybe for that, I'm just a little bit too conservative. We won't talk politics, but in terms of inventing new physics, I'm pretty conservative. If we can explain what we know about the universe without inventing new physics, I'd always prefer to not invent new physics
Yeah.
over inventing new physics.
Yeah, absolutely. And Speaker says, is there Planck length of time and why?
Is there a Planck length of time and
Mm-hmm.
why?
Mm-hmm.
Yeah, there is. There is a Planck length of time, and it's about 10 to the minus 43 seconds. The reason there is a shortest length of time is because if you try and ask questions about what does the universe do on time scales shorter than this, then if you try and calculate what type of quantum fluctuation would I get, remember for Heisenberg's uncertainty principle that there's an inherent relationship between an uncertainty in energy and an uncertainty in time. If you have a very small uncertainty in time, it means you have a very large uncertainty in energy. If you try and say what happens to the universe on a time scale shorter than the Planck time, the quantum fluctuations you look at, the energy fluctuations would be so large that it would make a black hole. This is bad,
Yes.
right? That's too energetic. You can't just say like, oh, we're going to get a fluctuation and boom, I've made a super big black hole. No, you can't do that. So we know that there's a fundamental incompatibility between general relativity and quantum field theory, and that prevents us from saying anything sensible on time scales shorter than the Planck scale of 10 to the minus 43 seconds, on length scales shorter than the Planck length of 10 to the minus 33 centimeters, or at energy scales greater than the Planck energy of about 10 to the 19 GeV, giga electron volts. The upper limit, by the way, to how hot the universe could have gotten if I convert it into giga electron volts is more than 1,000 times lower than the Planck scale. So when we say the universe never got arbitrarily hot, there's a really big drop from where the Planck scale is down to the hottest possible temperature it could have achieved.
That is so cool. Everybody's like, what's going on? So cool. There's so many good questions up further, but I was just reading the reactions there.
I think the bloody nose analogy really was a hit.
Yeah, I think it was too. Let's see. If you guys, if I
Scratch, don't
missed,
pick, kids.
yeah, now this will melt the brain. And so I had someone ask, what do you think? Which ways do you think the universe will end? Because there's so many ideas, like Big Crunch. Will it just keep expanding? People
Right.
ask that a lot.
So I gave you like the three scenarios where I said, we've got the big crunch, the
Right.
critical universe, and the big freeze. There is so right now, if dark energy is a constant, we are headed for a big freeze. We're just headed there faster than we would be if we had no dark energy. So it looks like in the far, far future, what's going to happen is all the galaxies outside of our local group will accelerate away from us and will disappear into the abyss. If we were born in our local group 100 billion years from now, we would not be able to see any other galaxies in the universe. They would have all sped so far away that you'd pretty much need to build a telescope the size of Earth to see anything beyond our local group. And if you don't see anything as you're building larger and larger telescopes, it's really hard to get the motivation to see that. It's interesting that if we were born 100 billion years from now, we would have concluded that Milkdromeda, what our galaxy will become, is the only galaxy in the entire universe. We're pretty lucky to be born when we are
Yeah.
right now. But there's another possibility that dark energy is changing over time. And if it does change over time, right, if it gets weaker and reverses sign, we could still get a big crunch. There's no evidence for this, but the people that I know, and these are mostly people about a generation older than me or more, who favored the big crunch before all the observational evidence came in, they say, oh, well, now I still favor the big crunch. This is kind of why sometimes we have the saying, which is based off of a paraphrase of something Max Planck said, that physicists don't change their mind. The only way scientific advances occur is one funeral at a time, because the old generation needs to die off for their bad, discredited ideas to die off. I hope that's not any of us, by the way. I hope that whatever we believe, when the evidence comes in and is decisive, we follow the evidence rather than our ideology or whatever it was that led us to think something else was more likely.
Right.
The other possibility is that dark energy will get stronger over time. And if that happens, if dark energy gets stronger and stronger over time, we will have a scenario called the Big Rip, where if dark energy gets stronger, then objects that are now gravitationally bound will not be bound in the future. So distant galaxies would get pushed apart, but then the outskirts of our own galaxy would get flung off. And eventually, whatever is left of our solar system will get flung out of the galaxy. And eventually, the planets orbiting all the stars will get flung out of the solar system. And eventually, planets themselves, and then even cells and atoms will get torn apart at the very end. That's the Big Rip scenario. Now, our observations are good enough that we can confidently say this isn't happening for at least tens of billions of years, many times the current age of the universe. But it's not ruled out, and it never will be. All we can do is constrain it better and better. I would bet on the big freeze, but we cannot rule out either the big crunch or the big rip as alternatives.
Yeah, the Big Rip sounds scary. The freeze doesn't.
I mean, it's all pretty scary.
It's all pretty scary.
I won't. I'll let you choose your own existential dread.
And Bantam says, so are relativity and quantum physics contrary or contradictory?
Oh boy, I mean, they're not really either. They're not either contradictory. The thing is, I like to think of them as complementary. They combined, they both explain the universe extremely well, but they don't give you everything. You cannot answer every single question with general relativity and quantum mechanics right now. Let me give you an example. If I were teaching a class, I'd ask for a show of hands, right? Not going to work. I assume most of you have heard of the double slit experiment, which means if you have like two tiny slits spaced narrowly apart and you fire one particle at them, it could be a photon or an electron or whatever you want, and you fire one particle at them, the particle will show up on a screen behind it. But if you look at the pattern it makes doing one particle at a time, you get an interference pattern where you have constructive interference and destructive interference and constructive and destructive and so on. It acts as though this single particle is interfering with itself. You get quantum interference of any particle that passes through a double slit. It's really weird. It acts like the particle is passing through both slits simultaneously. And it gets even weirder if you try and, mess with it because you want to know, damn it. So you measure which slit does it go through? And aha, it goes through slit 1 and the particle shows up on the screen. And it goes through slit 2 and it shows up on the screen. And if you do your experiment this way, you don't get an interference pattern. You get the particles that went through slit 1 and the particles that get through slit 2, and there's no interference. So this is part of quantum weirdness. So now we'll say, okay, I'm going to let this electron do its quantum thing. I'm going to pass it through the double slit, and I'm not going to observe which slit it goes through. I want you to answer this question now, which I don't expect you to answer because you can't, is what is the gravitational field of an electron as it passes through a double slit? You can tell me in general relativity what the gravitational effects are of a single electron, but you can't tell me what the gravitational field is for an electron described by a quantum wave function that passes through two slits. It's not defined, and this is because general relativity is not a quantum theory of gravity. It can deal with particles or point masses, but it cannot deal with a particle that's behaving quantum mechanically. So this is where we would need a quantum theory of gravity or something beyond standard quantum physics and general relativity. If we wanted to make a prediction for what's the gravitational effect of an electron that passes through a double slit or really acts like a wave in any way, we can't do it with our current laws of physics. So it's not like we're doing an experiment and this experiment contradicts what general relativity or quantum field theory predicts. It's just that we can imagine an experiment that our predictions don't make any sense for. And for those, if we want to make sensible predictions, we need a quantum theory of gravity.
Yeah, we also, I don't know if you saw it on Twitter, we did get a pre-question too, and I know that you're getting close to the hour mark. But someone said I won't be able to attend, so I was wondering if I can ask this already just now. And so it says, how does quantum pair appearance at the edge of a black hole, one getting sucked in and the other escaping? I think he's talking about those particle pairs. And yeah, he said, or even the one particle not getting sucked in cause a black hole evaporation. So he's talking about Hawking radiation.
Right. Okay. Quick answer is this is Hawking's analogy, right? Stephen Hawking was the one who said, like, visualize the quantum vacuum as particle-antiparticle pairs popping in and out of existence at the edge of a black hole. One falls in, one falls out. The one that falls out is your Hawking radiation, and that's where the particles go. Rest in peace, Stephen Hawking. That was wrong. That's not how it works. That is a visualization that is oversimplified and doesn't accurately describe the radiation for two ways. One, the radiation that comes out of black holes is mostly not particles or antiparticles. It's mostly photons. It's mostly just radiation, quanta of light of extremely low energy. Two, it doesn't all or even mostly come from just outside the black hole's event horizon. It comes from a volume that's within about 10 Schwarzschild radii of the event horizon. So it comes with a large area and it's almost all radiation, not particle-antiparticle pairs. What's really going on, and you have to go beyond the original naive explanation that Hawking gave to get there, is you have to use quantum field theory, and you find that it's actually the amount that space is curved that leads to differences in the quantum vacuum from what it would be over flat space. That's what creates the radiation. So that leads to an interesting prediction that actually lines up with what the theory predicts. The interesting prediction is that a smaller mass black hole, something that's less massive, because spatial curvature will be larger there, should actually emit more Hawking radiation and evaporate faster than a larger, more massive black hole. And this is true. If you did the calculations for how long would a black hole, like, let's say we turn the sun into a black hole, how long would it take for that black hole to evaporate via Hawking radiation, you get a number like 10 to the 67 years. Big number, but not the biggest number. Because if you looked at a really big supermassive black hole, like the one at the center of Messier 87, that's the largest galaxy with the largest black hole in our local supercluster. It's
Hmm.
at the center of the Virgo cluster. That black hole is about 6 billion times the mass of the sun, and it will take closer to 10 to the 100 years. It will take about 30 orders of magnitude longer for that to evaporate than the black hole in our solar system if the sun became a black hole.
Hmm. Yeah. So the stellar mass black holes would, evaporate quicker as opposed to these supermassive.
That's correct.
Interesting. So does that mean that all objects give off Hawking radiation just a lot
If
less than black
if you
holes?
curve space significantly, you should give off Hawking radiation. This is true. So everything should give it off. The problem is it is so mind-bogglingly weak, low in energy, low in temperature, that we have no way to detect it. How would you detect something that the radiation was so weak that you would need an antenna the size of the observable universe to detect it?
Yeah. And one more question, and then I can definitely let you get back because I don't want to take up too much of your time. There's just so many good questions. People have been waiting for this.
Mhm.
Alan asked, let's see, the ask him about not in a pseudoscientific new age sense, but because of collapsing the wave function, each particle in the universe depends on another for existing, thus providing the interconnectedness of everything.
The thing is, it's very easy to say, hey, everything in quantum mechanics acts like a wave. So maybe the universe is all connected, that everything's interacted with everything else, and it's all wavy. The thing is, when you make an observation, and observations don't need to involve human beings, they just need to involve particles of high enough energy interacting, or colliding or scattering off each other, something like that. That's good enough for an interaction. It doesn't need to involve you or me. Um, when that happens, many of the things that occurred in the past, um, they get erased. For example, there's this famous experiment called the Stern-Gerlach experiment. This is one of the first quantum mechanics experiments that you did. You pass an electron through a magnetic field in a certain direction, and the electron's trajectory will split depending on what its spin is. Now, until you measure it, an electron's spin is indeterminate. It could be plus a half or minus a half. I
Right.
can get my finger. Okay, plus a half, minus a half.
Uh-huh.
So you pass it through the Stern-Gerlach experiment, the electrons split. Then you say, hey, you know what I'm going to do? Instead of splitting it this way, I'm going to split it this way now. So the electrons split again, plus a half, minus a half, in the depth direction rather than the height direction. So they split in the depth direction, and now you take one of these and say, aha, now I'm going to pass it through the vertical Stern-Gerlach experiment again. And you would expect, because they split all up before, that all of these will split up, but they don't. They split in both directions again. By measuring it in the, I'll call this the Z direction,
Hmm.
you erased the information in the Y direction. You randomized it again. So you can get quantum entanglement between particles, or you can get this quantum weirdness going, but most of the new measurements you make will break that entanglement, and then things become unentangled very quickly. This is where the concept of quantum decoherence comes from, and why we don't see all these intertwined quantum effects on macroscopic scales. Because when you have large numbers of interactions occurring, it sort of washes out these quantum effects because they don't last. They
Huh.
don't survive from one interaction to the next, to the next, to the next, to the next. So that's kind of why this idea that everything is super interconnected, things are not as interconnected as someone like Deepak Chopra would have you believe. And the reason they're not as interconnected is because there are too many interactions that go on at a fundamental quantum level for all of these major quantum effects to carry through to a macroscopic scale.
Awesome. Uh, Everybody's saying these are the best explanations because this is so hard to do. And guys, this is the importance again of science communication. Someone said earlier, like when you're sighing, they're like he's explaining or trying to decide how to dumb it down, and it's really not. It's you have to understand these things, and way of understanding them is how you actually can talk to people about it. That's kind of the art of that. And you're so great at it. But thank you so much for your time. I don't want to take up any more because people are just going to keep asking questions.
Well, we'll just have to do this again when I
Yes.
have more time and you do another show.
Yeah, no, definitely. And so thank you so much. And guys, you can check out all his information. And can you just go ahead and just give the books, because I don't know if people know that you have books out already right now. It's in the
I
link.
do have
But
some books. Let me even see. I think I've got one of them right here. This is my latest book. It's called Treknology. It's about the real life science behind the technologies featured in Star Trek. I also have another book, which is probably on the shelf behind me. And this book is called Beyond the Galaxy, and it is a plain English version of what we know and how we know it about the universe, with about 150 illustrations, pictures, and you'll notice no equations. So you can read this even if you've never done anything other than look up at the night sky and know how we went from knowing almost nothing to knowing how we have our universe today with the Big Bang, dark matter, dark energy, inflation, right up to the present day.
awesome. Well, thank you so much for your time, and I'll be in touch with you soon.
All right. Thank you, Sky. Thank you, listeners. And I'll see you all soon.
Sounds good. Take care.
Bye bye.
Bye. So I'm still here, guys. And why is it showing that? I have no idea. Oh, wait, I do know. Just joking.